Hello, this is John Kavanagh from DMP Software, and this is a quick video on setting up your own analysis in Phast Micro. The tutorial is divided into two chapters. In this first chapter, you will open the example analysis provided with the program, explore its main features, and run the calculations, and view the results. The program is supplied with an example study folder called Phast Example Study, which is used in this chapter to give a quick introduction to the terminology and approach used in the program. To open the study folder, choose Open Example from the File menu. Go to Tutorials and open the Phast Example Study PSU file. The appearance in the main window changes when a study folder is open. There are many more toolbars, and there is a pane with 4 tab sections to the left hand side of the window. The pane is known as the study tree pane, and you work in its various tab sections to set up the input data for the analysis. The study tree pane allows you to organise and edit the input data for your consequence analysis. The pane contains a number of tab sections, each of which covers a different type of input data, and these tab sections are described below. Firstly, the model tab section. In Phast Micro, a model is a description of a particular hazard event that you want to process through consequence calculations. You define these hazardous events in the model tab section, and you can define any number in a particular analysis. As shown, the Phast Example Study folder has 8 different models, 4 describing releases of chlorine and 4 describing releases of butadiene. The model icons are organised in a tree structure. The top level represents the entire study folder with the name Phast Example Study. The next level is the study, named Example. The third level contains several folders, and the fourth level contains the models themselves. You can create any number of studies or folders depending on how you want to organise your analysis. To insert a model at a particular point in the structure, select the study or folder, and then select vessel or pipe source from the insert menu as shown. You can also insert a model by using the insert cascade at the top of the right click menu, or by selecting the icon for the model from the toolbar. The weather tab section contains a folder named Global Weathers with 3 definitions of weather conditions. The program performs a separate run of consequence calculations for each separate weather condition, giving a set of results that are specific to that weather. The Weather tab section also contains a study icon called Example Cases. In the Model tab section, all of the models have been placed inside the example case study, but you create and use any number of studies in an analysis. You can insert weathers underneath a study in the Weather tab section. Such weathers are known as local weathers, whereas those in the Global Weathers folder are known as global weathers. When the program is processing the consequence calculations for a given model, it will perform the calculations for every global weather and for any local weather under the study that contains the models. The Materials tab section contains 3 types of icon. A green icon which represents a pure material, a yellow and red icon which represents a mixture, and a pink icon which represents a pesticide. The Map tab section allows you to set up map images and geographic data so that you can view the regions and features affected by consequence results. The map image is defined by the power station raster image, and you can view the image by selecting Map from the View menu. The models are represented by dots on the map. These dots can sometimes be difficult to see and to relate to the individual models, but there are several options that can make this easier. You can change the size and colour of the dots, you can display the model name on the map, or you can pinpoint an individual model. To change the size and colour of the dots, select Map from the Preferences cascade of the Options menu. Move to the Model tab, change the default colour from turquoise to blue, and the point size to 10. OK the dialog. To display the model name on the map, if you move to the Models tab and select any model, and then select Labels from the View menu, the name of all the models will be displayed on the map. To hide the names, deselect the Labels option. If there is more than one model at a given location, as with the chlorine models and the butadiene models, then the name will be superimposed and may be difficult to read, although this will make it clearer that there is multiple models at this location. pinpoint an individual model, right click on the model, and in View, click on Pinpoint or press F4. The dot for that model will become centered in the map window and will also be highlighted. This allows you to locate a specific model, which is useful if you cannot identify the name for that model on the map. You can close the map window by selecting Close All from the window menu. We will now view input data. Move to the Models tab section and double click on the icon for a model. We'll double click on the chlorine rupture model. This tutorial does not attempt to describe every item on input data, but the program is supplied with a comprehensive online help. Every input dialog contains a help button at the bottom right. When you click on this button, the online help will appear in a separate window as shown. The help window will be displaying a description of the current tab section, but you can use the link inside a topic and the contents index and search tabs to reach any topic in the help system and gain a full understanding of the way the input data will be used in the calculation and the appropriate value that you should set for the hazardous event that you want to model. After you've finished exploring the input dialog, click on Cancel to close the input dialog without saving any changes you might have made. If you wish, you can move to the other tab sections and explore the input dialog for other types of data. We will now run the calculations and view the results. In the Models tab section, select the example case study and then select Models from the Run menu. The program will process the calculations for each of the 8 models in turn, performing the calculation for each of the 3 global weathers. When the calculations for a given model have been completed for all the 3 weathers, the name of that model will change from black to blue, which is the color coding that the program uses to show that the model has run successfully and has completed a set of results. The calculations will take several minutes to complete depending on the speed of your machine. You do not have to run the calculations for all the models. If you select a single model or folder, then you can run the calculations for just one model or for the models in that folder. We will now view the graphs for the chlorine and butadiene releases. Select the vessel or pipe source folder and then select the graph option. From the View menu, the right-click menu or the toolbar, a dialog will appear prompting you to choose the weather condition whose results you want to view. If you had selected a single model rather than a folder with multiple models, then the dialog would have checkboxes next to the weathers instead of radio buttons, and you will be able to compare the results for several weathers for that model. If you choose a single weather in this situation, then the graphs will have additional features that are not available when you are viewing the results for multiple models or weathers. For this example, select the f1.5 meter per second weather. This is the weather with the most stable conditions and is likely to give the longest dispersion distances. When you click on OK, there will be a pause for a few seconds, and then the graph window will open as shown in the space to the right of the study tree pane. The graph window will usually contain many tab sections, each with a different type of graph. The tab sections included for a particular combination of model will depend on the type of the material and on the details of the dispersion and effect behaviour. The chlorine models have graphs for cloud concentration and for toxic effects. Butadiene models have graphs for cloud concentration and for flammable effects such as jet fire, fireball, flash fire and explosion effects. The first graph is for central line concentration. This will be showing the results at the time at which the cloud footprint covers the greatest area, which occurs at a different time for each weather. The graph will initially be showing results only for the 4 chlorine models. In the dispersion calculations, the program uses an averaging time that takes into account changes in wind direction over the course of the release to give an average concentration at a given location, and it uses different averaging times for toxic and for flammable materials, reflecting the different timescales that are relevant to each type of release. The concentration graphs always display results calculated with a specific averaging time, which is displayed in the legend for the graph. The default averaging time for this set of results is the toxic averaging time, and the butadiene models were not modelled with that time, so have no results to display. To view the concentration results for the butadiene models, you must change the selection at averaging time to display. To do this, select Properties from the right-click menu or the Graph menu, and then move to the Averaging Time tab. If you change to the Flammable Averaging Time, the graph will display the results for the 4 butadiene models. The User-Defined option will also be enabled, which shows that some of the models have a user-defined averaging time defined in the Location tab section. In fact, all of them have such a time defined, and if you selected user-defined as the averaging time for the graphs will display results for all 8 models. After the 6 tab sections that show the results in terms of concentration, the next tab section is the map graph, which allows you to view different types of effect zones superimposed on the map. When you first move to the map tab sections, the map graph will be displaying cloud footprint results for a concentration of 10,000 ppm for the toxic averaging time, and the only results displayed will be for the chlorine rupture and chlorine liquid leak models. The other chlorine models don't produce this concentration level at the default height of ground level, as you can see from the side view graph. But if you open the plot property dialog, move to the distance tab, set the height to 10 meters, results for the chlorine vapor leak and chlorine relief valve model will appear in the plot. The footprint concentration results are the default form of results for the map graph, but the events field in the display tab section of the plot properties dialog allows you to change to a different form. The list of types of effect will depend on the types of models that are covered by the graph, and will be similar to the range of tab sections in the graph window. If you select Outdoor Toxic Effects, then the radiative/toxic field will become enabled, and you can choose between dose, probit, and lethality. If you view the lethality footprint, on the map, you will see that the chlorine liquid leak gives the greatest downwind effect distance for lethality. The rupture model produces higher peak concentrations at any given downwind location, but the short duration of the rupture means that the total dose received is lower than for the leak. The map graph initially shows the effect zone with a northerly wind, but you can choose wind direction from the graph menu on the right click menu to change the wind direction. The pool vaporization graph does not show any hazardous effect distances, but the toxic graph and various fire and explosion graphs all include footprint results of the form shown, and most of them also include graphs that show the effect level along cloud's center line as a function of distance downwind. If you look through the fire and explosion graphs, you will see that the greatest downwind effect distance is reached by the late explosion worst case for the butadiene rupture model, which reaches a distance of about 880 meters downwind. A late explosion is one that occurs after the cloud has started dispersing away from the release point, and by default the explosion is assumed to be centered at the cloud front, which means that the explosion radius will reach beyond the flammable region of the cloud. The program calculates the results for such an explosion at regular intervals, and the worst case graph displays the results for the ignition time that gives the greatest downwind effect distance. The program also presents results in the form of a report. If you wish, you can view a report that covers multiple models, but if you want to compare the report results for different models, it is easier to view separate reports for each model and compare between 2 reports. To view the report for the butadiene rupture model, select the butadiene rupture, then select View Report. After a pause of a few seconds, the report window will open to the right of the study tree pane as shown. The report window will probably hide the graph window, but you can use the option in the Windows menu to move between the windows. You can have any number of graph windows and report windows open at the same time. Similar to the graph window, the report window will normally contain several types of results presented in different tab sections. A given tab section will present the results for all the weather conditions that have been processed for the model. For the butadiene rupture model, the first tab section is the input tab section, which lists the input data. The audit tab section gives version details for the program, for parameters and materials, but all of the other tab sections give details of the consequence results that you saw summarized in the graph window. The summary report summarizes the maximum downwind distance to different types of effects and gives a direct comparison between the different weather types. For the butadiene rupture, d5 meters per second is the weather that gives the greatest distance, although the difference between the three weathers is small. The discharge report gives details of the discharge modelling and the conditions of the release immediately after expansion to atmospheric pressure, which is the condition used for the start of the dispersion calculation. This report, as well as all the other results, give the results for each weather in turn. The summary report is the only report which presents a direct comparison between the different weathers. The dispersion report contains a table which describes the location and state of the cloud at a series of time steps. You might refer to this report if you wanted to understand the particular aspects of the dispersion behaviour in greater depth. The commentary report highlights the main events in the course of the dispersion, and it allows you to see easily if and when there were different types of behaviour occurring, such as touchdown on the ground or the rain out of liquid droplets. The average time report gives the central line concentrations in the dispersion and commentary report, calculated using a core averaging time that is set in the dispersion parameters and that has a default value of 18.75 seconds. The averaging time report gives the central line concentration at a series of steps during the dispersion, calculated using alternative average times. For the butadiene rupture, these alternative times are the flammable averaging time and the user-defined averaging time. In this analysis, both of these times are also set to 18.75 seconds, so for all the butadiene models, the averaging time reports give the same concentration as the other reports. However, if you viewed the report for one of the chlorine models, you would see results for the toxic averaging time, and which has a default value of 600 seconds. The fireball report gives radiation results for a fireball resulting from immediate ignition of the release material. The report first gives a description of the fireball flame, emissive power, liftoff height. Then it gives the dimensions of the elliptical effect zones for up to 5 different radiation effects. And finally, the radiation levels at a series of points downwind from the centre line of the release. The jet fire and pool fire reports have a similar form, given the same 3 types of results. For the butadiene rupture, the tab for the early explosion report is named Early Exposure TNT, and this is because the explosion method selected for this model is the TNT method. The report is similar in form to the fireball report, giving the dimensions of the circular effect zone for up to 5 explosion overpressures, where the overpressures are set in the explosion parameter, and also gives the overpressure levels at a series of points downwind from the centre line of the release. The late explosion report gives the overpressure effect distance for late explosions occurring at a range of times during the dispersion. For each ignition time, the report gives the location of the cloud centre, the location of the centre of the explosion, the downwind distance to up to 5 overpressure levels, and the flammable mass in the cloud at the time of the explosion. The centre of the explosion is taken as the location of the cloud front to 50% of the LFL. The ignition time that gives the greatest downwind effect distance is the one presented in the worst case explosion graph. The range of reports presented for a particular model will depend on the type of model and on the behaviour of a release, and there are additional reports that do not appear for the butadiene rupture model. For example, if the material is toxic, then there will be a toxic report with a table of dose, probit and lethality results as a function of downwind distance. And if the liquid in the release rains out to form a pool, Then there will be reports describing the spreading and evaporation of the pools and describing a series of dispersion segments used to represent the vapour produced from the pools. For most of your work with the program, you will probably refer mainly to the graphs, since they present the results in the most direct form and allow easy comparison between different models and weathers. You have now seen the main features of Phast Micro. When you are ready, you should proceed to Chapter 2, which takes you through the stages in setting up your own analysis.